Hello and welcome everyone. My name is Tommy Hinks. I am lead research at Important Looking Pirates, a VFX studio based in Stockholm. Today we're going to talk about our ocean tools that we have used on countless productions. First, I want to talk a little bit about the background. These techniques are fairly well known in our industry, but it's useful to understand at least a little bit of what's going on. So these techniques that have been developed about 20 years ago, they talk a lot about how to make the ocean surface, how to displace it, but they don't talk so much about the geometry. So that's something we will cover today. And also, it's interesting how you can integrate these tools into your pipeline, and we want to show you how we have done that in a way that we think works very well. But before we move on, we want to show you some shots that we made recently, and it's not only ocean shots, but there are some very nice ocean shots in there as well. So in 2001, Jerry Tessendorf released some very nice course notes following the movie Titanic, where he describes how to generate synthetic ocean spectra. He did this by digging deep into the oceanographic literature, where he found some very nice methods for doing this. A couple of years later, Christopher Horvath found even nicer methods and expanded on these methods by adding some extra parameters and considering some extra things. The key mathematical idea is that if you generate the ocean spectra, you can then use something called a fast Fourier transform to convert those spectra into the spatial domain so that you can displace your geometry to get nice looking waves. As we see here in this picture, we can, using these methods by Tessendorf and Horvath, we can generate spectra. And here on the left side, we have shifted the spectra to have the zero frequency in the middle, and then we have the low frequencies just around that, and towards the edges we have the high frequencies. So we see that the highest amplitudes are in the low frequencies, which means that large waves, well, large waves are larger than small ripple-like waves. Yeah, and then if we transform this, we get a displacement map, which is basically how much to move each point on the geometry. So if we have a plane and we displace it using this map, we will get something that looks like an ocean surface. These displacement maps are tileable, given the periodic nature of the Fourier transforms. So even though we can tile them to sample them everywhere in space, it's common to use some tricks like cascading or noise masking so that we can avoid this repetition, because as the camera zooms out, it'll become very obvious and it's very annoying for the eye to see these patterns. Another thing we can do is we can treat the ocean as separate layers. This is actually very simple because we can just take different parts of the spectrum and treat them separately. So on the top row here, you see that we have only the low frequencies, which is like the swell waves. And on the bottom row, we have the high frequencies, which are the smaller ripple-like waves. And if we combine them, we get everything together. But we might want to have different effects for the swell waves and for the ripple waves. But this is something that I will return to this later, but it's very useful for the technical artists to be able to work with these two separately. So when the technical artists are often given reference material in the form of videos or images, and the director wants them to match this look and feel, so like certain characteristics of waves, certain wind, certain types of effects. And the artists are surprisingly fast at converging on the look, the creative directions given by the director, because of this multi-layer approach. Also, we should note that our approach is very similar to the one that Houdini uses, and we use it simply because it's the best one we've come across so far. Artists can also use masks and transforms, as I mentioned earlier, so that you can rotate or add noise to your surfaces, which also helps in the creative process. So even though noise doesn't follow the oceanographic rules, it's useful because, yeah, as in everywhere else in our industry, we don't want things to be too perfect. Now, Tessendorf and Horvath, they cover how to generate the displacement maps, and they do this in some detail, but they don't really talk about how to generate the geometry that you need to displace. I mean, you need something to displace when you have a displacement map. Very often, because oceans are very large, the ocean will fill the entire visible part of the horizontal plane. So whatever the camera sees on the horizontal plane should be covered by ocean. So we can use frustum techniques to try to do this, but there are some challenges here because the ocean can go all the way to the horizon, and we need fine details close to the camera, but we can't have like centimeter-sized triangles 7 kilometers away from the camera. The meshes would be too big. So we need a smoothly varying level of detail, which I'm going to talk about how we solve that problem. We also need good triangle quality, because what happens if you use a naive approach is that you get sliver triangles at the horizon. Those are triangles where all the vertices are on a single line and you can't shade them. The normals are not good. And we also need some way to control the resolution, because we also want to be able to generate preview meshes with lower resolution while modeling, and then we want to have very high resolution when we do the final renders. So one of the things that happens with displacement is that it changes visibility. So if you have a camera and you're looking at a plane, every point on that plane that you see maps to somewhere on the camera image plane. When you move stuff around, you're changing the visibility, and very likely you're making it so that in order to cover everything on the plane, you'll have to bring in points from outside the frustum and displace them into the frustum, or rather, points will be displaced into the frustum, and we have to find these points. The way we do this, we have an algorithm, an iterative algorithm that starts in the screen space, in the image plane of the camera, and then searches outwards until we have found all the points that map that get displaced into the frustum. This is an iterative process, but it's pretty fast in practice because we know when we're finished, and we can run every iteration in parallel. So it doesn't actually take that much time. On the right-hand side here, we see that we generate a mesh that is as tight as possible around the frustum edges. An important thing to note here as well is that we actually need to include points that are outside the frustum when we connect up the triangles for the mesh, since we need the actual ocean surface to intersect the frustum planes. Otherwise, we would end up with very, very tiny gaps that would appear as noise around the edges of the screen. So we were talking about level of detail earlier and how we want smaller, a denser tessellation close to the camera, smaller and more numerous triangles, and then we want fewer and larger triangles out off to the horizon, right? Where we have large areas in world space, but that are very small in screen space. A naive approach is to cast rays from every pixel in the camera, but as I mentioned, you end up with triangles that are very elongated, and they even become what we call sliver triangles. So we want to avoid that, and the way we do it is we make a lookup table so that when we cast our rays into world space, we see, oh, did we make a bad triangle? In that case, we need to find a new position in screen space to sample from. So we can use a cycle of projecting and back projecting until we can guarantee that the triangles are close to unilateral. And this is what we're showing in this zoomed in view here. It's a little bit hard to see, but that the triangles are well behaved even though they're quite far away from the camera, which is at the apex of this triangle that you see here. This method is very nice because the artists don't have to worry about anything. They just point the camera and then they get their ocean plane. Triangles are nice. They don't have to worry about displacement around the screen edges. Their job is to focus on the characteristics of the waves. So are they moving fast enough? Does the wind speed look okay? Or all those kind of things. The geometry should just work. So, integration. How do we get access to all these tools? So, for modeling, which we do in Houdini, we hijack Houdini to propagate our ocean parameters in a sub-context, and everything is flowing through the graph, just like normal Houdini primitive attributes. So all our parameters are visible. You can interact with them. You can write Python code or VEX code. So the artists are able to create their own custom tools based on like a small minimalistic core that we in R&D provide, which is good because they don't have to come to us every time they need an update, because then they might have to wait a couple of days, so they can just do it themselves very quickly in production. We've also focused a lot on VEX integration, so we can access all the ocean properties inside of VEX. This, as I will talk about on the next slide, it's very useful for setting up simulations. But it is also useful for previewing meshes in Houdini, where you get kind of a low resolution geometry, and then you can displace it using VEX, but you can also add color channels, like if you want to see the normals or you want to see the velocity or other things like that. We have tried different approaches with trying to write custom deformer nodes, but we found that it's impossible to anticipate everything that the technical artists are going to want to do. So instead, we just give them VEX. Now, simulation. So almost every interesting scene consists of something other than just a procedural ocean. There's some object crashing into the water surface, making a big splash, or there's a maelstrom or a whirlpool or whatever. There's always something else going on, right? So we need to have a good way of merging the simulated water surface with the procedural water surface. So By doing that, we don't have to simulate the entire domain. We can keep the simulation tightly bound around the interesting parts. And this is where VEX comes in again, because you can set up the simulations, you can inject the velocities into flip simulations very, very easily without having to create any geometry. You can just go straight to the VEX, and with the positions in space where you want to know the velocity, you can just sample it there. And you can also sample something called cresting that we mentioned before, which is a measure of how much the waves are self-intersecting when the vertices are being pushed together horizontally to get the sharp cuspy waves. This is very nice because as waves break, air and water mixes, and that's where you get bubbles and spray, and then you can generate those interesting effects that kind of separate VFX water from like games water or other more simpler approaches. So for rendering, we instantiate the geometry at render time. So we don't actually send huge meshes over the network to the render farm. Instead, we send a description of our ocean parameters. So this is just a JSON blob, a text file. This saves a lot of disk space, and it also saves a lot of network bandwidth, and the render time to first pixel becomes much shorter because of this. We can choose if we want to instantiate the ocean mesh already deformed, or if we want to displace it as part of the shading. So inside the Arnold shaders, you have access to all the ocean properties again, like the cresting, the velocity, the displacement, everything you might want, even normals if you want to do bump mapping inside the shader. This is very nice to have this flexibility, because in some cases you just want to deform the mesh and everything is kind of fine. In other cases, you want to tweak it a bit inside the shader, you can do that too. If you tweak it too much inside the shader, you might end up in a situation where you realize, oh, I need the actual final displacement somewhere else, like some object is floating on the surface. So you need to be careful. It's a trade-off. Future work. So we would like to support more DCCs. So right now we're supporting Houdini and Arnold, but the way our tools are structured, we can we have the plugins are very thin, and they're just talking to a core, just passing information in and out. So we think that it should be doable. And one idea is to have the oceans in Maya, where animators might benefit from being able to see the surfaces. Also, of course, USD Hydra. We could potentially support everything that supports USD. Also, we have found that in some cases, when we are merging simulated meshes with the procedural meshes, that if you don't stitch them into a single mesh, you can get some rendering artifacts. So it would be nice to figure out a way that we can merge them into one mesh to avoid some types of shading artifacts. That's all we have, folks. Thank you very much for watching. We have put a special ocean reel up on Vimeo, and please note that there's a password there. If you have any questions, please contact us on Instagram or through our webpage. Thank you, Haley, for organizing this fantastic event, and thank you to all the pirates for turning technology into beautiful images.